Hello everyone, this is Sky speaking. Welcome back to the course. This chapter, I will talk about arithmetic datapath. So in this chapter, we will cover this topic. We'll first look at the commonly used arithmetic operators such as adder and subtractor. Then we will study multiplier, divider. At last, we will take a look at the operation on real number. So for the first three parts, we will operate at the integer number. Before we start, I want to tell you the key point of this chapter. This is an important chapter, and the key point is, for the first, you have to understand the delay and area difference for each architecture of the adder. These are the architectures for the same function adder. So you have to understand the area and delay difference of these architectures. This is the first key point. The second is you have to understand the idea behind these architectures. Then you can use you need to understand the idea and use these ideas in your circuit design. Okay, you need to use the idea behind these architectures in your circuit design. So this it's not important to remember the architectures to implement adder. They have been implemented by some old engineers and they are well designed. So there is no need for you to repeat. Okay, you just need to use the idea. Okay, let's go on. First, I will give you a small exercise to warm up. We have introduced the function of max of 2 bits. Okay, that is 221 max. So can you use the 221 max to build a 421 max? That is max data of 4 input bits. For example, you have 4 input bits of D, range from 3 to 0, and you have 2 bits of select. Yes. So when cell equal to 0, choose the output is this bit. When 3, the output is this bit. So can you build this architecture? You can take out your pen and papers and try to draw some figures on your paper. Okay, you can pause the video. I will show you the result. This should be something like that. Yes, this may be obviously for you. So now just check for this item. Cell equal to 0, that is cell is equal to 2. Okay, so this is equal to 1, this bit equal to 0, so this path is cut off. Okay, so this is cut off. Yes, so the data can pass through in this way. Okay, so this is exactly the function we need for max. Okay, suppose you have get the right answer, and you can wrap the cell up to make it a 4-bit max. Okay, you can give a symbol for the whole circuit. So this symbol will be a 421 max. Then you can note it. You can note that the architecture is something like a twin binary architecture. Sorry, is something like a binary tree architecture. Yes. This is the root, and each node there will be 3 leaves. There will be 2 leaves. Okay, 2 leaves. This is the node. This node has 2 leaves. Node, 2 leaves, 2 leaves. So this is a binary architecture. And the topography of a binary tree will match the topographic of data convergence. Data convergence. What is data convergence? That is, you have many inputs, many inputs such as 4, 8, 16, 100 maybe. While after the calculation, you just have 1 or 2 outputs. This is data inputs, and finally you have 1 or 2 outputs. They are converged to 1 or 2 outputs. So you can say the tree architecture, the binary tree architecture will match the topography of data convergence. Data convergence. Okay. And be noted that except binary tree, you can have a tree with three leaves. Okay. A node with 3 leaves. You can have a node of 4 leaves. Then this will be a chord tree. Okay, just not be limited. Okay, just not be limited. You have to open your mind. Okay. Okay, we will go to our this chapter of arithmetic functions. First, we will look at one bit for under. This is a question for last chapter. Have you finished that? This may be the answer to the question. Using a 4-bit adder has 3 inputs, A, B, and carry in. You will calculate 2 outputs. Each variable is 1 bit wide, so you will have sum and carry out. The algorithm we use there is we first calculate P and G. P means propagate. That if you have 1 in carrying, the logic can propagate the 1 to C out. So this means if you have A or B equal to 1, you can propagate. Yes. And we calculated for G. The function for G is you can generate carry out. You can generate. That is, if this is 1 and this is 1, and so you can generate carry out. Yes. Then we calculate for sum. Sum is exclusion all of all 3 bits. Okay. At last, we'll combine G, P together to get C out. To get C out. So C out may be propagate, carry in, and or generate, carry out. So this is a function, or you can say this is a gets. You have to use to build the 1 bit for AND. Yes, you may say, oh, this is different from what you have told in last chapter. Yes. Sorry. Yes. We have told you can use the truth table. the truth table. Okay, the truth table to calculate the final equation for any logical function. But there you will use some other method. I think the two must be equal. After simple of the functions you get from truth table, you may get something like that. Okay. The 1-bit full adder, if you have to code in Verilog, maybe something like that. Okay, maybe something like that. This is a Verilog code. If you don't understand the Verilog code, it's okay. Just take it as C code. Okay. I will introduce Verilog language in next chapter. And in Verilog, you typically there is no need for you to write this statement. You just write a simple line like that. And the EDA tool will synthesize the code to the logic gates. Okay, the EDA tool will understand the meaning of your statement and translate and use logic, the basic logic gates in the cell library to build the same function as your statement. Okay, so this process is called synthesis. Translate until Q to get level late list. This is always done by EDA tools. So that's why there is no need for you to implement an adder. Okay, this is done by EDA tools, by synthesis tools. Okay, by the way, if you omit this input or you type this input to 0, we call this is a half adder. Okay, because you missed something of the input. This is a half adder. Okay, if you have a 1-bit full adder, okay, this is a 1-bit full adder we have learned before. Then you can build adder for any bits. Is that right? So this is an example of build 1-bit, build 8-bit full adder using the 1-bit full adder. You just cascade them up. Cascade them up to get the 4-bit, to get the 8-bit function, 8-bit adder function. So this is simple and obviously, but there is some problem for this circuit. Yeah, this is a delay. You can see the signal here, the signal of bit 0 need to propagate from this to this point. This is usually 8 level delay of a 4-bit adder, of a full adder. Okay, so the delay is usually, the maximum delay is usually 8 level of 1-bit full adder. So this may be a problem. If you want a 32 bits adder, this will increase, the delay will increase. How about 64 increase? Okay, so some engineers will think about, can we shorten the maximum path for adders? There is any method or architecture or algorithm we can use to shorten the path? Yeah, they do come out some architectures. Yeah, they do come out with some advanced architectures. So before we go on, let's first define a symbol. Okay, a symbol for 4-bit adder. This is a symbol for 4-bit adder. They carry out a sum and the inputs, AB inputs. Okay, this is a symbol. The symbol represents for 4-bit 4 ender. Okay, let's go on. The first I want to introduce is carry select. The architecture name is carry select. It's something like that. Okay. Let's first talk about the idea. The idea for carry select. That is, you calculate all the possible cases. Yeah, I don't know which one you write, but I calculate all the possible cases and choose the right one. Select the right one and last. Choose the right one last. So you can say for the first 4 bit, you just use this simple 4 bit ender. Okay. Well, I don't know this say out of the fourth bit. The first bit. I don't know if there's a 1. How to calculate the higher bit? You don't know. So you can guess. You can try all the possible cases. That is, we enter 4 bit ender here and guess the C-in is 0. Also, we have a 4 ender guess C-in is 1 and calculate the amount at this point and this point. And finally, when the value of this point is valid, when this point, the value on this point is valid, it will propagate to the cell pin of the marks, and the marks will sell the right value from the two guessing ender. Yes, the value, this value is guessed, this value is guessed. The say out is also, the carry out is also guessed. Then we'll choose the right one. So this is the architecture. You can pause the video to have a detailed look at the diagram. The point is guess all the possible case and select at last. So if you are ready, we can analyze the delay of this architecture. So this is the delay is here from bit 0 to here. This is a 4 bit ender. Okay, this is no problem. Well, you can see for this part of logic, they can calculate parallel. Okay, these 3 can calculate parallel. So this means when the value at this point is ready, the value at this point should be also ready. Yes. So the total delay will be the delay of this ender plus the delay of marks. Yes. So this is the total delay. This is the total delay for this architecture of 8 bit for ender. Now you decrease the delay from 8 level of 1 bit to 4, and then plus a small delay of marks. This is really a big advance, a big improve. Okay, by the way, do you think my speech is a little better now? Sometimes, and for this chapter, you may can't follow, you understand, you may can't follow my speech now. Yes, if this is the case, you can pause the video, okay? Okay, although the the delay is much better. How about the area? The silicon area, or the logic gates it's used, compared with the repointer. You can say repointer just has this part. This part is additional and. So you can say the area is nearly 1.5 times. Okay. Why 1.5 times of the repointer? A little more. So data and the delay and the cost of area. Okay, as I have said, we just focus on the idea behind the architecture. So using the idea of carry select, how do you architecture the function for this code? The function is simple. Compare the value of a, b. They are both 32 bits. Then you can calculate the output. If a bigger or equal than b, you need to calculate the AND function of c and d. If not, calculate the AND function of e and f. So can you draw some figure of this function? Yeah, you can do some figure like that. Okay, no need to too detail as that. Yeah, just a little abstract. Just a little abstract is okay. Okay, if you're done, I will go on. So, if one architecture, maybe the same as the code says, you need to compare. Okay, you may need a subtractor. We will talk about it later. You may need a subtractor to compare the result of A, B, then select the value. Okay, according to the result, bigger or equal. If yes, you will select C and D and do the AND calculation. If not, you will select E and F, then do the AND calculation. Yes, this is an architecture. If you analyze, the delay will be the subtractor through the marks, then through the AND. Yes. So it seems this architecture has nothing to do with carry select. Okay, has nothing to do with the idea of carry select. Can you improve the delay? So this is another architecture. We can guess. Yes, we don't know the relationship between A and B, so we guess them all. We calculate C, D, E, F along with the AND operation, the sub operation, then select the right one. When the sub is stable, the output of the sub is stable. Okay, there is an assumption. This 32-bit sub function usually has the same delay as, or linearly the same delay as AND function. Okay, so the delay of this part usually is balanced with the delay of this part if they are the same bit values. So this architecture, we use the idea from carry select. We guess and seal and select the right one at last. So you can come. The delay for this is the delay of this subtractor, then plus the delay of the marks. But the area is bigger. Yes, this is the additional area for AND function. So you can come out of the conclusion. Okay. Okay, that's all for carry select. Let's go on with. Okay, if you have you need a reset, just take your reset. No, if you need a rest. Okay, if you need a rest, just take your just stop for several minutes. Okay, let's go on with carry look ahead. This is another architecture engineers has designed for AND. The idea behind the carry look is look all the inputs as a whole. And try your best to calculate the critical path, to calculate the signal on the critical path. So for AND, who is the critical? You can say, from the point you can say, this signal. Yes, this signal is the critical path. Is the critical signal. That is the signal with the biggest delay value. So the idea is we will take all the inputs as a whole, and try to calculate the output, the critical output, as fast as possible. This is the ideal, and usually we can use a logic of 3 levels to do all the complex logic calculation. Yeah, just with logic of 3 levels. Do you think this is impossible? No matter how many inputs you have, or how complex your logic function is, we just use 3 levels of logic. We can do the function. Do you think this is impossible? Is it impossible or impossible? Okay. Remember the function continuous 0. The function continuous 0. We have said you can use the truth table and write function like that. Yes. Write the equation for each bit yields 1. So in this part, you just have 2 levels of functions. Use inverter and AND. And if you have many inputs, if you have more inputs, the AND is always that is the AND will be AND game of 3 inputs or 4 inputs or 6 inputs or 100 inputs. Yes, but they are all AND functions. Then you can add them up to get the final value. So this is a 3-level logic. The first 2 is the inverter and AND. The last is the OR. Just the difference is, okay, the complex is you have used the AND gate or OR gate with a lot of inputs. Yes. So this is usually possible by using a bigger inputs gate. Okay. Or you can say a gate with many inputs. Okay. Okay. Remember the idea. Look all inputs as whole and try to calculate the critical signal using 3 levels of logics. Okay. Let me explain the current look ahead for give you a simple explain. If you don't understand the following part, it's okay. First, we'll calculate the G and P equation. This is the same as the full under. And then we will calculate the C out. This is also the same as we have learned before. But in the following picture, okay, the symbol used to denote and or is different. It uses the dot to denote AND function and use the AND to denote the OR function. Okay, the notation is just the symbol used is a little different in the following figure. In the following figure, you have to notice. Let's come to the equations. Let's go to the equations. So the C1 for first bit is simple, and this C2 is the equation for C2. Maybe it's something like the generator of bit 1 and the propagate of bit 1 and the carry in of bit 1. Yes. The two equation is something like that. Okay. Then you just use the binary algebra. You replace the C1. You replace the C1 with this. Okay, you replace C1 with this equation and expand the round brackets. Okay, and use binary algebra to expand the round brackets. So you will get the equation like that. Okay, for bit 3 and bit 4 is something like that, just a little complex. So at last, you can get some function like this function we have said before. You get a lot of all AND gate with many inputs, and all them together, all gate at last to get the final result. This is something like that. Okay, the PG is some. The PG itself is some simple gates. Okay, that's all for the explain. So the equation here, if you replace the AND dot to logic gate, it will be something like that. The PG, then AND them together, all the item together to get the final output. So for this picture, just ignore the Chinese characters. Okay, ignore the Chinese characters. You just look at the figure. This is a 3-level logic. Okay, this is something different from what I have said. We have said we have used inverter and OR to form the 3-level of logic. Okay, there is something different, but the idea is the same. Maybe they have some optimize at this part. Okay, so you can see this the 4-bit under the delay is always three logic. But in the ripple and what's the delay? In a ripple, you can say it in a. It's also okay. It's also three. Okay, it's also can be a three level of logic. But this three logic use the input cell. The cell input is always 2 bits. 2 bits. Yes, 2 bits. Three level of logic with all cell is a 2 bits input cell. All cell is 2 bits. All cell with inputs of 2 bits. Okay. All cell with inputs of 2 bits, but for this, you will have inputs of 3, 4, 5. Yes. 3 level, but the input is bigger. So you can say for ripple it should be 12 level of logic, but of simple logic with all cells with 2 bits input, with 2 bits. Then we just have 3 level of logic, 3 level, but the some cell with bigger inputs, right? With bigger number of inputs. Okay. So actually the 4-bit input cell usually has bigger cell delay than the 2-bit input cell of the same type. They have bigger input, but totally the total delay should be smaller than the ripple under. Okay. The total delay should be the 3 level of many input gate. The delay of 3 level of many input gate should be later, much shorter than the delay of ripple under with 12 level of logic. Okay. That's all for the look ahead under. It's okay if you don't understand the equation. Okay, you don't understand the equation is okay. You can try it at your time. You can figure out the equation at your time, but this you must understand. The tool you must understand, and you can master the tool. You can master the idea and use the idea. Let me give you example. The function is if you want to find the first bit that equals to 1 in a 16-bit input such as D. The order is from least significant bit to maximum significant bit. That is from 0 to 15. And if you occur the first bit 1, the first bit equal to 1, then you stop at there and output the bit index. Okay, and output the bit index. So the output should be 0 to 15. If all the bits are 0, all the bits in D in are 0, you just output 0. So this is a function. How will you architect the circuit to implement this function? Just think about it. You can pause the video, okay? You can pause the video. You do need to exercise yourself. Oh, sorry, I have give you some tips. So the simple and obvious method is test the input bit one by one using max. For example, if D is 1, you will choose this path. This path is cut off. The 1 will be the output. Yes. So if this is 0, and this is 1, this path will be cut off, and this path will be on. Yes, path will be connected to the output, and this is 1. This input is 1, so this value is passed to the output, and this is cut off. Okay, so you can use 16. You can use 16 marks to implement this logic. Just cascade them one by one. So the delay would be 16 level of 2 input marks. Yes. Then can you improve? Can you improve? Using the idea of carry look ahead, take all inputs as a whole. Calculate the delay critical path first. Try your best to calculate the delay critical path. Okay. This is my answer to this question. We can divide the 16 bits input to groups. Okay, this is group of 2 bits, group of 4 bits, group of 8 bits. Then we will find the first one in each small group. Then use the binary tree architecture to select the right one from the output, together the output. From the lower level of group to the higher level of group. So the calculation, they find the first bit one in this group, in this small group is parallel, and this group, the group of 4 bits is parallel, the group of 8 bits is parallel. Yes. Just when you calculate when you select for example, when you select the output, when you select the value, the bit location or the bit address at this point for the lower 8 bit, you have to check. Yes, I want to explain this. You have to check the value of 4 bits as a whole. Yes, to select, you either select the result of A or either select the result of B to its output here. Is that right? You take the 4 bits as a whole. to either select the result from this point or from this point. If you want to get the result of the final result, you will take this 8 bits as whole and choose either the C result or D result from this point. Yes, this is the ideal group, and make it a binary tree, and take some bits as a whole to do the design, or you can say to calculate the select flag. Okay. So we can change the serial cascade architecture to the tree parallel architecture. So the function for this check how to do it. You may use the equal to 8 equal to 8 bit 0. Okay. So this is a simple variable code for this architecture. You can read it. For example, this is a file. This is a file select. We check the lower 8 bit to test whether it's 8 bit 0. If this is true, the first 1 bit must come from the higher bits. Yes. So this is a test. We use the lower 8 bit, take it as a whole to test whether it are all 0. If this is true, the bit equal to 0 must in the higher 8 bit. So if this is not true, so the location, the bit equal to 1 must be from the lower bits. Okay. So this if else design equal to this point, equal to this point. Equal to this point, check there, check this. Okay. Check this point to decide we choose the value of C or choose the value of D, and append a higher bit. Yes, append a higher bit 0 or a higher bit 1 to the value. Yes, this is append. Okay. So for the lower 8 bit, for each group of 8 bit, I define a function to calculate. The idea is the same. Check the lower 4 bits if this is calculation for the higher 4 bit. No, sorry. This is the calculation for the lower 4 bits within a 8 bit. This is the calculation for the higher 4 bits within a 8 bits. So this is exactly matches the tree architecture. Okay. If you don't understand this page, it's okay. Okay. I will introduce the VLSI language in next chapter. This is just a simple example of showing. This is an example that shows how to use the idea behind cell A carry look ahead. This example may be not good enough. Okay. Okay. For the same function, do you have any other good algorithm, a better algorithm to deal with it? For example, if you need to find the first bit 1 for a DE of 32 bits or 64 or 128 bits, do you have any? If the inputs of the bits of the input increase, is there any better architecture or algorithm? Okay, just try it. Just think about it. Okay, is there any faster? Can we go even faster than carry look ahead or carry select? Or can we improve the area of carry select? Yes. Engineers or scientists come to some solutions, such as BK and some Cogstone, KS and they are already triangles, usually in the form of binary tree. Okay? They are using triangles. And the delay of this triangle is usually around this number. Is usually around this number. That is one delay of 1 bit for enter. Plus the delay plus the delay of max multiply the bits of k equal to the bits of the input. For if you use the sensor bits input, the k equal to, if you use the 32 bits and okay, k equal to 32. So this is the cell means round to the bigger number, round to the big integer, round to the big integer. So how this equation comes out? You can think about the carry select example. Yes, you can think about the carry select. In this figure, we are 4 bits based. Okay, can you use a 1 bit based carry select architecture to build a, such as to build a 2-bit adder? Then you can use it to build a 4-bit 8-bit 16 32-bit. Okay, if you use 1 bit as the basic cell, so you can come out with this function, with this equation. Okay, you can come out with this equation. Okay, just try it by yourself. Okay. Oh, there is a simple question for you. Question: assume the minimum delay. If we use them a fast architecture of adder, we can get a delay of 5 nanoseconds for the sensor, for the 32-bit adder. Then if we increase the input bitwise and using the same cell library, that is the same cell, the two use the same cells or the cells with the same delay, using the same cell library, what's the minimum delay we can get for this function, for this 64-bit adder? What's the minimum delay? A, B, C, D. Which one is right? Which one will you choose? Okay, my answer is C. There is some hint for you. To solve the problem, you have to read the two hints first. So let's assume the max delay is something equal or nearly equal to the PG function delay. And the max delay and the full under delay is 2 times of the delay of max, of 2 input max. So you can get an equation 2x and x then equal to 5. Yes, this is dot multiply. This is x. So you can solve this equation. X equal to what number? Then you can have an equation like that. Yes. Then multiply x value. This is x value. So then use this, replace x with the real number. You can get the value. You can get the delay value for the 64-bit adder. Okay, so don't be scared. Okay, double is not right. Okay, the delay can't be double. No change is also not right. Just increase a little. You need increase the delay nearly the delay of a max or 2 input max. Okay, that's all for adder. We have introduced 3 types of adder: ripple adder, carry select, carry look ahead, and have a test of some 3 adders. Keep this in mind. You just need to understand the delay and the area of each architecture, and the most important is the ideal behind each architecture. You need to use this ideal for your circuit. So, adder. What about subtractor? How to build a subtractor? There is actually no subtractor in digital circuit. They all use adder. This is because in digital design, a computer or the whole computer system, by default, we use the 2's complement form to represent signed number. Yes. So if you don't know 1's complement, 2's complement, you have to refer to the books of computer architecture or books of digital design. Okay. This part will be told in these books. So for subtractor, if you want to do A sub B, the output value must be signed. Yes, must be a signed value. Or should be signed value. So the sub can be looks like something that add a negative value. Sub equal to add a negative value of B. And the negative value of B can be changed into the 2's complement form. Yes. So that is invert all the bits and plus 1. This is the function of 2's complement. Change the negative number to its 2's complement format. Then use an AND. This is just several inverter in parallel, and you can take this as a carry in. Yes, the carry in, of 0. Then use the ANDer to do the subtract. So usually the ANDer or the subtractor, the delay of ANDer and subtractor is usually the same. Is usually same if the input bitwise is the same. Okay. Okay, that's all for subtractor, and that's all for ANDer and subtractor. And at this point, you are able to do the arithmetic calculation at about your first or your second year at primary school. Yes, you can do the mathematical functions of your first or second year and at your primary school using the digital circuit, using digital circuit. Okay, that's all for this section. In next section I will introduce the multiply and divider, how to use digital circuit to do multiply and divide. And you can think, by now you can do AND, then multiply is and divide is simple. Yes. From the mathematical view, from the view of mathematics, multiply can be built from ANDers. Yes. Divider can be built from subtractors. Yes. Okay, let's end here. Thanks.